Hello, so welcome to yet another lecture. And then this particular lecture will be focusing on memory cache, the memory cache in computer architecture. So, yeah, by way of brief introduction, we do know that the computer actually uses different types of memory. In fact, they are in a level of hierarchy. We have the level one, two, three, and four. And then that is what a computer actually uses in order to facilitate processing, storing, and the retrieving of data during processing by the CPU. So on this particular lesson, we'll be focusing on the memory cache and how it aids in the performance of the CPU and how it generally aids in the retrieving of data. So by way of introduction, that what is the memory cache? We'll be coming to that, but before that, let's have a look at the different levels of memories that we have. So the computer system actually uses a memory hierarchy to balance performance, cost, and then capacity. So then from the diagram we are seeing here, we have the registers being the first, they have the fastest, the smallest, and then they are the ones located inside the CPU, followed by the memory, the cache memory that we'll be focusing on in this particular lecture, the main memory, and then the secondary storage. The secondary storages are usually the external read devices, the SDD, and then, but then focusing on this pyramid or on this diagram, we notice that as we move down the hierarchy, the distance to the CPU actually increases. That is how close that particular memory is to the CPU actually increases. Number two, the capacity, that's the storage capacity of the particular memory also increases. And then the speed, however, this is the disadvantage, the speed decreases. So moving down this pyramid from registers to memory cards um to the external final one, the RAM and then the secondary memory, closeness to the CPU increases. That's the distance between that particular memory and the CPU increases. The capacity, the ability of the memory to store data also increases. But then how fast it is, the speed actually increases. So on this particular lecture, we are focusing mainly on cache memory and then how it actually operates. So what is cache memory? What is cache memory? So the cache memory is actually a small high capacity storage area. It is a small high capacity storage area very, very close to the CPU and from which data is accessed. So what the computer actually does is to store data that will be frequently accessed by a running program on this cache memory. So for example, we have this game playing. These are high games that requires a lot of storage capacity in order to install on the programs. Various examples of game. But then we do realize that the main memory requirements of these games, however, are very, 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 very small. Now, in running of such a game or any other large program on the computer, what a computer actually does is to store the essential part of the data that will be required in playing or running such an application on what we call the cache memory, so that they are easily retrieved by the computer or the CPU whenever they are required. So we say that they are small, high speed storage area that stores frequently accessed data and instructions. And then they act as the buffer between CPU and then the main memory, the main memory, the main memory. So back to this illustration. So imagine playing such a huge game and then the computer needs to calculate the position of characters, or let's say where the game has reached, and then the computer needs to process the position of characters. They retrieving such data from the main memory will cause the computer to slow down or will take quite a long time. And hence the introduction of what we call the cache, the cache, the cache. The cache. So what the cache then does is to store copies, smaller copies of these data, which will be frequently used by these games or by any other high program on the cache. So it stores the data, frequently used data from the main memory location. So a better illustration will be here. So we have this in the main memory location for the particular program that is being run. And then this processor needs to access data from the main memory. But then the main memory in this particular case actually will give this data to the processor in a very, very small, slow mode. So in order to avoid that, what we do is that this card will fetch this data from the main memory and store it here. So that anytime the processor has needs of this data, the card just delivers it to the processor. So in doing so, we reduce the processing time, or we reduce the time of fetching the data from the main memory and head back speeding out our process, speeding up our process. So we'll take this as an example. We'll take this as an example. So we have a game ongoing, and then we need to access, or we have any program running, and then the processor needs to access data from this bit or from that bit. Moving from the processor and then fetching the data from the main memory or the secondary memory will cause, it takes quite a long time to do that. Therefore, to reduce the average time, what a computer does is to make copies of this data that will be required and then store them on the cache. That's the frequently data that will be used by the particular program will be stored on this cache and then delivered to the processor whenever they are in need of use. Whenever they are in need of use. So this concept of cache actually exists mainly because, or is made possible mainly because of what we call locality of reference. Locality of reference. That's what we'll be looking at very soon in our next. We will be looking at the locality of reference. But before that, we will take a look at this, the cache performance. Cache performance. What happened? So we have this here, and I'll be simulating very soon to illustrate what we mean. So when the processor makes a request from the main memory, when the processor makes a request from the main memory, the first thing that the processor does is to search for this data that is requesting for from the cache. And then if it finds that data, we say we have a cache hit. When that data that the processor is requesting for is found, we say we have a cache hit. But in most cases, when requesting for the data for the very first time, especially when running a program for the very first time, this data that we are requesting for will not be here. So in that case, we say we have a cache miss, a cache miss. So then what happens is that the processor would then go ahead and fetch this data from the main memory, give it to the cache, and then it will now be delivered here. I'll try and simulate, run that simulation very, very soon. Yeah, let's run that simulation very soon. So the main concept of the memory works this way. So we have data stored on the RAM that needs to be given to the CPU. But then the CPU requesting for this data from the RAM will take quite a long time and it will actually slow down our process. So what happens is that we'll make this request, the CPU will make that request from the cache. And usually when running a fetch program, the data that we are requesting for will not be on the cache. So we say we have a cache miss. Why? A cache miss in the sense that the data that we are now requesting for does not exist on the cache. So let's go ahead and simulate. The data that we are requesting for does not exist. So when it's request for the data from the cache and we do not have it, we say we have what we call a cache miss. A cache miss. Now, when the computer takes notes of the fact that it has a cache miss, what does it do? The address of the particular memory from which this data will now be fetched will now be kept in the cache. The cache will now keep this address so that in future, and not just that one, it will keep closer all nearby addresses in the RAM. It will not, we are now making a request from this, but then the cache will go ahead and fetch this data, the address that we are requesting for, and then go ahead and fetch all other nearby addresses. Why? Because it knows we will be using them sooner, and we'll be discussing that when we get to the locality. It knows we will be needed them very, very soon. So when we now deliver this data to the CPU, and then in any near future, we make another request for a data, because this cache has already fetched all this data now, the nearby data, we will now have the data that the CPU is requesting for, and then we say we have what we call a cache hit. A cache hit. Simply meaning that the data that we are requesting for now exists. How and why does it exist? Because when we made a first request for this address, the cache was smart enough to pick up all other data stored in the different addresses here, and they've been stored here temporarily. So that whenever the CPU now makes a request for this particular address, the cache already has it. And we are going to have a cache hit, making our work much more smoother, much more smoother. So that's by way of simulation, a brief explanation again. If the processor finds the memory location in a cache hit is said to have occurred. However, if the processor does not find the memory location in the cache, a cache miss has occurred. That is, we have missed the data. So what then happens is that the cache then goes ahead from the simulation we just did. The cache will then go ahead and pick up that data and all other nearby locations or addresses in the RAM and then store it, knowing very well that the CPU will make a request of this particular data sooner or later. Sooner or later. So we say, what are some of the characteristics of a cache memory? The characteristics of a cache memory, let me try and zoom in so we can all move together. A cache memory. So this process of fetching data from the RAM, keeping it and delivering it to the CPU, it's a very, very fast process. So we said that cache memories are extremely fast. Why? Because they act as a buffer. They act as a go between the RAM and the CPU. So the CPU does not have to jump in searching for data from here, but then it goes directly to the cache to get this data. So they are extremely fast. Number two, they hold frequently requested data in instructions, and thereby ensuring immediate availability to the CPU. So whenever we are working on any program, the cache memory knows what data will be immediately requested or what data is frequently requested by the user or by the particular program, and it's immediately kept in that cache and then delivered to the CPU It is, however, a bit costlier than main memory, but more economical than CPU registers. Now, having dealt with cache miss and then the cache hit, we'll move on to what we call the locality of reference, which is also a very, very important concept that we need to look at. And we have two main types of locality of reference. The first one, we have the temporal. Let me zoom out so we have the temporal locality, and then we have the spatial locality. We'll be simulating these two as well. So for the temporal locality, it deals with a concept that recently accessed data is likely to be accessed again. What do we mean? Now, when the cache picks up data from the main memory, it knows that this particular data that was just picked up will be requested again. So the cache keeps it so that the CPU does not have to come back to the main memory and make a request of this. And that's what referred to as the temporal locality. So with the temporal locality, it keeps the recently accessed data, knowing very well that it is likely to be accessed again. It will be kept in the cache locality. And then an even more interesting one is the spatial locality. What happens here is that the data, any other data, physically close in memory will also be accessed around the same time. So when we make a request for this particular data, the cache does not just pick this data, but it goes ahead to pick any other close data, knowing very well that they will all be accessed sooner or later. Let's try and simulate that. Let's try and simulate that as well. Yeah, so let's try and simulate that. So over here, our CPU is making a request for a data from this RAM, from this particular address. But what happens is that the cache will go ahead for the temporal locality instead of allowing the CPU to take this from the RAM, which will make the whole process very, very slow. The cache picks up this particular data that we are making a reference to. And then not just that, goes ahead to pick up any other data that we'll be needing. Any other data. So we say every data which is physically close will also be picked up or be accessed at the same time whilst it is accessing or performing the first process of the temporal locality. So this is the address we made reference to be kept in the cache. In temporal locality, that address will be kept. But then using the spatial locality, it goes ahead to pick up all other data close to this particular data that we made reference to. So that in future, whenever the CPU makes requests for this data, that data will already be in existence. That data will already be in existence. And then we do not have to go through the long process of having to wait for that data delivered to us. So that's basically what happened. Now, the cache there actually has three main levels. And that's the next thing we are looking at. The cache actually has three main levels. You have the level one cache, referred to as the L1. We have level two, L2, and then obviously, definitely level three, which is the L3. How do they work and how do they help in making our work very, very easier? So we'll take a look at the first one, the first level, which is level one cache. So basically, the level one cache is a usually they are integrated in the CPU itself for the level one cache. I'm using the red to represent the cores of the CPU. The CPU may have a dual core, an octa core, etc. So for the level one cache, you have them embedded or you have them integrated in the CPU itself. And because they're already in the CPU, they operate at a very, very, very fast rate. So the L1 caches are the fastest of all the caches that we have because they are embedded or they are integrated in the CPU and hence they operate at a very, very fast speed. At a very, very fast speed. They're able to store data from 2 kilobyte to 64 kilobyte. I'll be showing a table to illustrate that as well. Followed by the level two, the level two cache, the level two cache, the level two cache. And for the level two, they can either be within the core of the CPU or they can be outside, depending on the particular system we are using. They can either be within or they can be without. They can be separated from it or they can be within. And they are also shared across all the cores. If they are without, which means they are shared across all the cores of the CPU. And they are also connected with a very high speed bus. That's when they are outside, they are connected with a very high speed bus of the to the CPU in order to run very fast. They are very fast, but then slower as compared to the level one cache, which are integrated within the CPU itself. Now, the third level is what we refer to as the level three. The level three. The level three, they are typically usually outside, and it is not all processors that use this level three. So they are usually used by higher end processors. What they basically do is to enhance the performance of the L1. So what the level 3 does is to enhance the performance of the L1 cache and then the L2 cache. So that's basically what the level 3 does. It is also shared among, once it's outside, it is shared among all other cores of the CPU. It is definitely slower than the level 1 and then the level 2. However, this rate of being slow is even much faster than the RAM. It is lower compared to level one and then level two, but then this rate is even much faster than a RAM, than the RAM. So we'll go ahead. This should be a brief summary of what we did. So the level one caches are small, they are fast, making them that expensive. Level two, they are medium sized, their speed is moderate compared to the level one cache, and their cost is mid-range, not too expensive, and then not too cheaper too. Level three, they are large, they are slow, and we are using this slow relatively, comparing them to level one and level two. They are slow when compared to these two, but then they are faster than the RAM, and their cost, they are the least expensive of the three that we have. And then I have them tabled nicely here. Level one cache, the size they can carry 32 kilobytes to 64 kilobytes. Level two, 256 to 1 megabyte, and then level three, 2 to 50 megabytes. The fastest of them all is the L1 cache, which is level one. Level two, bit slower than level one, but faster than level three. And then level three is slower than these two. What level three does is to enhance the performance of the first two, but then it is also faster than the RAM. Level one is located or integrated in the CPU core by way of um, CPU core by way of breakup, and then level two is a shared core. When they are outside, that when it's placed outside, it is shared between or among the cores, and then connected to the core with higher speed bus. And level three is also shared among the cores as well. So basically, this will be a recap of the memory card system of the CPU. How does it function? We have the CPU with caches inside or within, trying to request for information from the RAM or from our secondary memory. The first time it tries to gather or to take this information, because it is the first time we are running this particular program, we will not be able to fetch this data. And then we say we have what we call a cache miss, a cache miss, a cache miss. But then it goes ahead, whenever we have a cache miss, it goes ahead to then fetch the data that the CPU requires and keeps it in the cache. So that the next time this data is requested for from the CPU, we will then have what we call a cache hit. Why? Because the data will now then at the time of being requested for would then be within the cache, and then it will be accessed by the CPU. Accessed by the CPU. So basically, that is how it works. Let's look at the importance of having this kind of system. The importance of having this kind, the cache itself. Let me try and get rid of this so we can actually deal with it nicely. So in conclusion, the cache memory is a very, very critical component in modern architecture. Why? It bridges the gap between the CPU and a slower main memory. We know that the main memory is very, very slow. And when we refer to the main memory, we are referring to the memory from which the program is being run. So what the cache does is to bridge this gap, the speed gap between the CPU and then the slower memory, keeping data that will be frequently accessed by the program on the cache, and therefore increasing our processing as a whole. Number two, it exploits the locality of reference. Not forgetting we've dealt with two main localities: the the spatial locality and then the temporal locality. And it exploits these two types of localities in order to improve the performance. It is also organized in three main levels. We looked at level one, level two, and level three of the cache levels. And it uses sophisticated mapping techniques to optimize data placement. This lecture is not on mapping technique. We'll be looking at mapping technique in the subsequent lecture. But that is the importance or how essential the memory cache is. To the extent that without the cache, processes will speed, without the cache, the speed time of processes will be very slow in the sense that they will have to wait for data. and thereby creating a severe bottleneck in system performance. Therefore, the cache memory helps to speed up the process of fetching data from the RAM, from the main memory, and thereby increasing our total throughput. This will be our lecture on cache memory. Thank you very much.